look at 3.4, which is probably the most dense of the sections in chapter 3. The first few talk about quadratics, a little bit more about polynomials, graphing them. Those tend not to be too bad. We've looked at quadratics quite a bit by now because we've looked at it in chapter 1 when we were solving, in chapter 2. In chapter 3, we're really looking more at polynomials, so ones that are even greater than a second degree, that we want to be able to chop them down so that they are a string of what we call linear factors, a bunch of x plus some things, x minus some things. But we're okay if it turns out that we have a quadratic because we got that lovely quadratic formula. So the problem is that polynomials are not, you can't just look at them and be like, oh, obviously it's going to factor like that. So what we do is we have a couple of formulas and a couple of theorems to help us out. And one of those is the rational root theorem. Now, the rational root theorem in theory is great. In use is a little bit tedious. Basically, what you're going to do is you're going to look at your leading coefficient and your constant that's at the end, and you're going to find the factors of the very last term, that constant term, and factors of the leading coefficient, and then one by one you're going to divide them out. One of those, if you have rational roots, and you most likely do, the rational root that you find has to be one of those guys. So the example on slide 4 is just list all the possible rational roots, and I have f of x is equal to x cubed minus a 3x squared minus a 4x plus 12. So now the cheat is to graph these things. If you graph this, you can see from the graph where it goes through the x-axis. X-axis, where those intercepts, those are the solutions, which are zeros, which are roots. They're all just different ways to say the same thing. Now, to prove this by hand, what you would do is you could actually factor this, and then you come down and you find the rational roots. Or if we wanted to go ahead and just list the possible rational roots, we could say, all right, let's find factors of 12. And factors of 12 would be 1 times 12, positive and negative. You have to use 2 times 6, 3 times 4. Luckily, this is a 1. So all of these over here, one by one, will be divided by this positive or negative 1. So my possible rational roots would be positive or negative 1, 12, 2, 6, 3, 4. And you can see that the positive 2, the negative 2, and the positive 1 are in here. So these other guys are just extras. And it comes from, all these extras come from the idea of factoring, right? How did you factor? You found factors of the last and the factors of the first, and then you use those guys to kind of make this, to fill in the blanks in those parentheses. Well, like I said, it can be pretty long. The other one wasn't too bad because the leading coefficient was a 1. When your leading coefficient isn't a 1, then you have a lot more solutions. So we have factors of 3, at least that's prime, and I only have the 2, the positive and negative 1 and 3. But now factors of 6 would be positive or negative 1, 6, 2, and 3. And so one by one, you're going to take these, and I know I kind of write it backwards, but you're going to divide by your ones at the end. So we're going to kind of go like this. 1 divided by 1, 1 divided by 6, 1 divided by 2, 1 divided by 3. 3 divided by 1, 3 divided by 6, 3 divided by 2, 3 divided by 3. So these are all my possible rational roots, but I can kind of clean this up a little bit, right? A 3/2, that's a 1/2. I already have that. I'm sorry, 3/6. That's a 1/2. I already have that down here. 3 divided by 3 is a 1. I already have that down here. So if I were to graph this, the rational roots, if I were to find any, would definitely be one of these. Those are the only choices that you have. Sometimes, and basically this is what we kind of use this for, is if I want to know what the roots are, I want to solve the polynomial, I can use a combination of theorems like the possible rational root theorem and the one that we're going to look at in a couple of slides called the fundamental theorem of algebra, which basically says that whatever your degree of your polynomial is, that's how many roots you're going to find. Now, that doesn't mean that they need to be unique. So, for example, the one we were just looking at, this has 4 roots. There's going to be 4 solutions. Now, these solutions could be 2, 2, 2, 2, right? It could be the same number 4 times. Or it could be that some of them are imaginary, and there's another property to kind of go along with that. And if you were to graph this f of x that I have right here, it only looks like there's 2. So is it a situation that this negative 1-ish type looking guy, and maybe that's a 2, are those duplicates? Are those multiplicities of 2, right? So I have the 2 2 times, and I have the 1 1 time. Well, we know that's not the case, right? Because it's going through. So this appears either 1 or 3 times, and this one appears maybe 1 or 3 times. But we don't know until we break the whole thing down. So I know for sure from this graph that one of my real roots is a 2. I also would have pulled that out from the possible rational root theorem because I have factors of 18, 1 by 1 divided by this 1 out front. So it would be positive or negative 1, 18, 2, 9, 3, 6. I think that's all of them. So without the calculator, you'd have to say, well, let's choose a 9. Let's choose a 3. Let's choose a negative 1 and synthetically divide 1 by 1 till you come to yet another theorem, which is called the factor theorem. If your remainder over here, when you're synthetically dividing, is a 0, then you know that this is a root, well, which we knew already from the calculator, that if this were equal to x, if you kind of undo that, so you set it equal to 0 again, then that thing is a factor, and what's left over is a factor. So because I did my synthetic division, where I said, okay, I'm going to synthetically divide by the 2, so that I had drop the 1, 2 times 1 is 2, add down. 2 times the 1 again, 2, add down. Times the 9, 18, add down. Times the 9, 18, add down. I know I get left with down here, this is my remainder, this is my constant, my x to the second, my x to the third, and you would count your way up. What it kind of does, that synthetic division, is kind of divide for me. It helps me factor. My puppy's barking, very barky this morning. So I know now another way to write this f of x is x minus 2 times this quantity over here. Kind of like 2 divided into 6 is 3, right? So you knew this. You know that 3 times this is equal to that. Same thing here. It just kind of goes backwards. This times this gets you back to that original f of x up there. It's all upside down, like everything else in algebra, right? So I'll rewrite this, and then I can say, oh, look at right in here, I can do a factor by grouping, where I pull an x squared out of the front and a 9 out of the back, which leaves me with an x minus 2, x squared plus 9, x plus 1. Well, here are my 2 rational roots that I had, multiplicity of 1. But it's a multiplicity of 1, right? Nobody's 3 times. It's not like x minus 2, x minus 2, x minus 2, x plus 1. I have this guy hiding in here, which is going to create imaginary roots, right? Because I'll have x squared plus 9 equal to 0, which is going to be an x squared equal to a negative 9. And when you solve for x, you get that positive or negative 3i, which leads us to yet another formula. Somewhere. And maybe it's in the next one, but it's a play off the rational root theorem, and that is the irrational root theorem that says imaginary roots, complex roots, or irrational roots have to come in conjugate pairs. I'm out of room up there. Have to come in conjugate pairs. So if you have a 3i, conjugate, I think that's how we spell it. So if you have a 3i, then you know you got a negative 3i. If you have 2 plus radical 3, then you got 2 minus radical 3. These guys have to come with as buddies. And that is because at some point, if you did that, use the quadratic formula, which you know is this. And it's this guy right here that causes the conjugate pairs. So this says just list the rational roots. I would have factors of 8 divided 1 by my factors of 1. Well, that's easy. And so I have 1, 2, 4, and 8, that guy. You'll use this in 3.5 to find f of x. So in 3.4, you're finding roots. In 3.5, you'll have the roots and you'll want to find f of x.